Hello, Mr. Kersey here. We're going to be looking at how a heat is gained and lost from a system. So to get this started, let me walk you through what we have material-wise. First off, we have some hot water. Basically, mine is boiling, but it doesn't have to be quite boiling, but should be relatively hot. Do please be careful with it because you do not want to get burned. This could be, mine is on a hot plate. You could heat this on the stove. You could heat it in the microwave. How you heat it is not super important. Just, again, do treat it with caution. I have a secondary container. In this case, I just have another beaker. I have 10 pennies. Now, my pennies I made sure were from prior to 1980, because that way they are higher copper content and don't use as much zinc. Whereas modern pennies are primarily zinc and have just a coating of copper. I have some cold water. I've got my thermometer. I've got a scale, and I've got a timer. And then I've got some tongs so that I can fish them out of the hot water, and we're going to place them in here. All right, so first thing we're going to do is we're going to weigh the mass of our pennies. So I'm going to take my pennies, and we are going to place them on the scale. So I have, again, 10 of them. And they weigh 30.8 grams. So it is important that I make note of that. So I've created a spreadsheet to kind of help out. And we know the total mass of my pennies are 30.8 grams. In addition, I've already looked up some heat capacities. So if you look back here, there are two specific heat capacities we need because we're using pennies. Pennies are made out of copper. We looked up the specific heat of copper, which was 0.385. And then the heat capacity of water is 4.186. Both of these are going to be important. And if you don't know what material you're using, because it does not have to be pennies, you can use any other object, but you will need to probably Google and figure out what heat capacity is based on what the material is made out of. So once I have that, I'm going to go ahead and take these pennies and carefully place them into my hot water. So I'm going to put all 10 of them in and try not to splash on myself. And I'm going to go ahead and start my timer. So we're going to leave them in there for approximately 2 minutes. But while that's going on, we're going to prepare for the other part of the experiment. So I'm going to take my beaker that is empty, has nothing in it right now, and we're going to weigh it. So in this case, it is 64.1 grams. So on my spreadsheet, we're just going to write the value, 64.1 grams. And we're going to add some water to it. Now, the amount of water is not critical. It's better not to fill this up all the way. You want to give it enough to where it's going to cover the pennies. But if there's less, you're going to see a bigger change in temperature, which is what we want to do in this case. So I'm going to go ahead and put approximately 40 milliliters of water. But again, it does not really matter how much I have. So I ended up a little bit over 40 milliliters. But we're going to put it back on the scale, and we're going to weigh, and this time we're at 101.3 grams. So now to figure out how much water we have, we're just going to take and subtract 101.3 minus the mass that we started with. And in our case, we're going to end up with 37.2 grams of water. So that's going to be important later when we're doing our calculations. In addition to that, we're going to need to get the temperatures of both our hot water and our cold water. So we'll go ahead and do our cold water first. So in this case, our cold water is approximately 8.6 degrees, which again, we're going to record that as well. 8.6 degrees Celsius, and I am measuring everything in Celsius. It is important that you use the same units and that they match that of your heat capacity. If our heat capacity uses Celsius, we want to make sure we measure our temperatures in Celsius. Okay, our pennies have heated up long enough. We're going to leave them in there a little bit longer because we're not quite done taking temperatures, but you want to make sure they're in there at least 2 minutes. We also need to get the temperature of our water that is boiling, so we're going to go ahead and do that right now. So we're going to take this, just kind of spin around our thermometer, and we are right around 97 degrees. So 97 degrees. And all right, so Next up, we're going to take our pennies and we're going to remove them from the hot water and we're going to place them into our container. Hold on one second. When you're doing this, you want to try and make sure you are getting the pennies out as best you can, and you don't want to get any of the, you don't want to get excess water out with them because that will throw off your results. If you get a little bit, it'll be okay, but just keep in mind that you do not want to have that happen. And you want to do this as quickly as you can. All right, once I get all of my pennies in there, I'm going to go ahead and just put a piece of glass on it to cover it up, and we're going to let it sit for 2 minutes. So the reason we're waiting 2 minutes again is we're just going to make sure that there's plenty of time for all of that energy from the pennies to transfer over into the water that we have in the cup. All right, it has been 2 minutes, so now we're going to take the temperature of the water. So if we look here, we can see that the water temperature has definitely gone up. In our case, it has gone up to approximately 17.3 degrees. So we're going to take that and record it as well. So we're going to end up with 17.3 degrees. All right, so now that we've collected all of the data that we need, now it's time to do a few calculations to figure out exactly how much heat was transferred when we took the pennies from the hot water and transferred into the colder water. So if we go up here to the screen, you can see I've kind of laid out the equations we need and just set it up ahead of time. So what we have is we have Q, which is going to be our total energy that is going to be transferred, is always going to be equal to our mass times the heat capacity of whatever material or medium we have, times the change in delta T, which is change in temperature. So in our case, what we're going to need, this is this setup for the water, and this will be for the copper. So let's go back and look and see, well, our water, we know the mass of it because we recorded it earlier. If you remember, we got 30.8 grams when we weighed the pennies on the scale. So we're going to go ahead and put that here. So 30.8 grams, and this is going to be times, and these are all, again, multiplied together. And then our delta T, so again, this is the amount that the cold water changed. So if we go back to our, we have our mass of our pennies. The amount that I apologize, we did that incorrectly. Again, if we're looking at the water, we do not want to have the mass of the water. We're going to have the mass of, well, we don't want the mass of the pennies. We want the mass of the water. So over here under the copper, that's where we're going to put the mass associated with the pennies. Over here with the water, we're going to put the mass associated with the water. So if I go back to my sheet, we have 30.8 grams, which is how much copper mass we have. So if we go to our sheet, that'd be 30.8 here. And if we look at our mass of water, the mass of water in cup 2 is going to be 37.2. So we're going to go 37.2 grams. And then we're going to have, again, our delta T. Delta T is just the change in temperature. So it'd be our final temperature minus our initial temperature, which in this case, our final temperature of the water in cup 2 is 17.3 minus 8.6. So 17.3 minus 8.6. All right, so this one's all set up for me to get my calculator and calculate it out. Let me finish setting this one up so that I can just calculate them both together. So in this one, our delta T is not going to be the temperature of the water, but the temperature of the pennies. So the pennies started out at a temperature of that was the same as the boiling water. That's why we left them in there for 2 minutes so that they could equilibrate and get the same temperature as the water. So our pennies are going to have a temperature of 97 degrees as their initial, and their final temperature is going to be the same as that of the water of the 17.3. So it'd be 97 minus 17.3. All right, so then this would be where I get my calculator. And again, we're going to hopefully remember in math, we know PEMDAS. So we're going to do the parentheses first, and then we just multiply across. So in my calculator, I'm going to go 17.3 minus 8.6, which gives me 8.7. And then I'm going to multiply that by 4.186, and then multiply that by 37.2. And we're going to end up getting 1,354 joules. And again, on my calculator, obviously it went on for many more decimal points, but you're going to have to round, and rounding to the whole number in this case is reasonable because 1 joule was a very small amount of energy. Now we're going to calculate the other one, where we're going to end up with 97 minus 17.3. And then that gives me 79.7. We're going to multiply that by 0.385, and then multiply that by 30.8. So in this case, we got 945 joules. All right, so if we're looking at our system, so this would be how much energy was transferred by the copper, and then we look at our total energy that the water got. So lastly, if we want to figure out how efficient our system is, we're going to take our 945 and divide it by 1354, and then ultimately we're going to multiply it by 100. So on my calculator again, we're going to go 945 divided by 1354, which is going to equal 0.697, so times 100, which basically is going to give us that we are 70% efficient. So 70% of the energy that was transferred ended up going into the water. Now we might ask ourselves, well, what happened to the other 30%? But this is where you need to look at things such as heat loss due to the surroundings. We are not in an insulated container, so again, we have our glass, and we did put a lid on it to try and stop some of the heat loss. But again, there's always going to be some unless you use very specific means to try and minimize it. But anyways, that is showing how energy was transferred from one system to the other.